Yeah, hi all, welcome to my channel. So this is basically video on like ongoing series of like Java concurrency. If you didn't watch the previous videos, I'll put the link in description, so please go and watch. So where I basically explain everything very in detail with most demoable concepts with a lot of code as well. So in this video, we're going to discuss about like volatile and atomic, like understand the differences between volatile and atomic and when to use when. And also we'll see about real world scenarios as well in this video. So Java provides a mechanism to manage. So what exactly, why this volatile and atomic is comes into picture, right? Because of a concept called memory visibility problem. So what exactly is memory visibility problem? So basically whenever a thread, whenever multiple threads parallelly accessing a data of a shared data, it is possible that thread 1 updates something and thread 2 might not see that value. Like that's nothing but a memory visibility problem. Like basically every thread has their own cache. Because of that one, thread 2 still see the old data only, and it might lead to the inconsistency. That's why it's all everything this volatile and atomic comes into picture, like because of this memory visibility problem. So Java provides a mechanism to manage memory visibility and atomicity issue across threads. So if one thread updates the data, so it should make sure that all the threads should get the data, like that visibility should be there for across all the threads, and it should be instant. It's not like after some time, right? It should be instant. This mechanism this mechanism can be provided by the help of volatile keyword or atomic classes like atomic integer or atomic boolean. We'll discuss each thing in depth. As I already discussed about memory visibility problem, threads can cache variables. When thread A updates a variable, thread B might not immediately see the change if it is working on a cached copy. If thread B is working on its own copy, if thread A is updated its shared variable, then thread B might not see the thread A's updates, right? That's where the all shit comes, right? So the lack of visibility can lead to inconsistencies or incorrect behavior. So how the caching happening in threads, right? There are like three levels are there. One is basically processor caching. You know, right? In a modern applications, modern CPUs has hierarchical levels of cache: L1, L2, and L3. Um, that are basically close to the processor rather than a RAM. So whatever updates in the RAM, that is basically visible to everyone. But this modern application maintains the hierarchy of caches, right? But for various performance reasons, like so these caches stores copies of data from memory that thread is likely to use. For example, in a multi-core system, so thread A is present in the one core and thread B is present in the one core. So then what will happen? So whatever data updates by thread A might not see by the thread B, right? Because it's updating a different core. So since each processor core has its own cache, two threads running on a different core might see different copies of same variable. So one is happening at a process cache level, and also when it comes to write buffers, right? CPU might also basically CPUs uses called write buffers to temporarily hold the write values before it write back into the cache or memory. So even before writing into the memory, CPU holds the some temporary values or all the write values or most recent write values in the write buffers. Like later it will basically insert push to the memory, and this delay will cause the visibility problem, like and also compiler optimization. So compiler also might reorder the instructions based on the program we written. It's converted to assembly level and the very low level coding. That's why basically it will reorder the instruction. That is also possible that because it assumes that everything happening in a single threadedly, but it is not aware that things are happening in a multi-threaded environment, right? That needs to be handled by the application level itself. So these are the this is how basically data can be cached in a various levels. So now I understand what is volatile keyword. So a volatile keyword in Java ensures that changes made to the variable. So if you are basically mentioning, for example, a value, for example, boolean flag equals to true, flag equals to false. If one thread if you keep that under, if you mention that variable as a volatile, so then what will happen? If you update something for one thread is basically update the flag is set to false, then all the threads will basically visible, that one, that the data will be visible. So here volatile is solving that memory visibility problem. When a field is declared as a volatile, the compiler and runtime are put into notice that variable is shared and changes made should not be cached or optimized. So which is changes made on a volatile, it will directly read to the main memory. It will directly read to the, it's stored in a memory. It should not be cached or it should not be optimized. So that would prevent the threads from seeing its true state. So volatile ensures that every read of a volatile variable will be read from the main memory only. That is the main important thing. And every write to a volatile variable will be write to the main memory only. So here what's happening, whenever you mention a variable as a volatile, it is bypassing that local cache thing. So whatever you are basically storing the values, everything happening in a main memory itself directly, like. And next thing, atomic operation, right? So okay, we have volatiles, and why you to use atomic operation? So atomic operation also performed as a single independent individual step. So sometimes, for example, volatile basically gives that. So volatile solves the memory visibility problem, but sometimes that data, it is not a boolean variable. Let's say it's a basically integer variable. So you want to increment that value. You want to perform, let's say, atomic operation, like for example, if you mention a counter plus plus, right? What exactly is the counter plus plus? First it reads the counter, then it basically writes the value to the counter and updates the counter value, right? Which means here it's happening in two operations, read and write. That both are not a single step. It's a multi step, but according to indication, it's single step. So these things, volatile solves the memory visibility problem. But when it comes to this atomic operations, this volatile won't solve the this update data. Like it will solve the reading problem, but it won't solve this updation one because of the atomic operations. So atomic operation executed on a one single machine level operation. So what it will do, whatever you are performing on, whatever you are keeping that variable atomic operation, it is assumed that it's happening in a single operation, which means a single threaded operation, right? Ensuring that no other thread can intervene during that operation. That's where it will solve these compounding operations as well. So what is difference and use cases, right? So memory visibility with atomicity. So volatile ensures that updates to a variable are propagated periodically to other threads. However, it doesn't provide atomicity for compounding operations, for example, like incrementing. So atomic classes are ensured that both visibility and also atomicity, like so atomic variable will ensure that both visibility and also atomicity for operations and performance, right? Obviously, like as atomicity is not taking care of volatile obviously like higher performance when compared to the atomic operation. So volatile is generally less expensive than locking, but more limited its functionality. So whereas atomic class strikes the balance of providing atomicity as well as visibility as well, without needing any synchronization. Here we are not performing any synchronization, like we are not keeping that increment operation under synchronization, but we are utilizing the atomic operation on top of that. Like that's remove the synchronization and also balance the both visibility and atomicity, and also performance also most optimized one. So, but it's slightly more overhead than volatile due to some more complex atomic operations they support, like. So use cases of volatile, right? So use volatile when you ensure visibility of changes to the variable across threads, but does not need to perform compounding operations. Simple thing, like an example is basically boolean flag to stop a thread, right? For example, if one thread sets the variable, okay, exit true, if let's say other threads basically processing, they might process, like, but due to its volatile nature, other threads also see, they will also basically set that, okay, it is true, then let's exit, like they all don't perform this if block because of a true. And use case of atomic class basically when you need to perform atomic operations like incrementing a count rate without using a synchronizer block or methods. So it can be more expensive and can lead to the contention sometimes. So real world scenario, suppose you're building a server application where thread pool a boolean field to check if server is basically still running or not. So here in order to check a server is still running or not, the multiple threads parallel accessing, but a flag can be set a false to signal all the threads to stop running, right? Here a Volatile is sufficient because just updating the flag value and needing the immediate visibility. That's where you can use the Volatile one. But when it comes to, for example, this example, consider an example that counts the number of visitors in a website. For example, many people comes to the website, right? It's a basically parallel operations like. So now, basically each visitor increments a separate event, right? Each visitor increments is a separate event. So it's a possibility that multiple parallel events can generate it because of multiple visitors will happen. So using an atomic integer ensures that increment operation is atomic and prevent of any loss of visitor count due to the concurrent access. That's where you can perform, let's say, okay, visitor is unique plus plus. So that's where you can perform, you can put it in atomic operation. It will prevent because of this concurrent issues like, and also it solves the memory visibility as well as it's an atomic operation. So that's where we basically has the atomic and volatile. So before going into the next session, let's code it. Okay, now let's create for example shared object, um, private boolean flag, right? Flag, and maybe let's generate um, now let's do this getters and setters. Now what will happen, let's have a main method. So let's say shade object, right? So thread one object dot set flag to true. Thread 2 new thread object dot get flag. Okay, is flag. You can pass the thread 1 dot start and thread 2 dot start, right? So here what's happening, basically one thread is basically setting an object and one thread is basically accessing an object. Sometimes it will be possible. For example, now I'm assuming like basically it's always prints true because it's a happening one after one, right? But in the so it's always true only. But if you are having a more load, more concurrent way, then sometimes it happen that all it might not always false. Like it might not you might not see always true. So that's where basically it's basically happening the memory visibility problem. Like you can. For example, let's keep set flag is false. Let's thread 3 dot start. Let's see what will happen. Like true. because it might start early, that's why it might get true. Yeah, I think because of for now it's accessing synchronously, like because of like very low data, it's happening very fast. Ideally, it should be like thousands of 100 iterations. Then basically we need to keep this a volatile, which will make sure always this set object will be visible to the other threads, like especially accessing in a shared context. So this is the what basically we call as basically memory visibility problem for the volatile. And you can also think about atomic integer, which we already discussed previously. Let's say counter object. Let's say counter only. Um, int counter refactor generate, right, generate constructor counter and getter counter. Now let's have a main method. Let's create a counter object. Counter equals to, okay, you need to do increment also, right? So that's actually the issue, like generate setter. Okay, I think maybe we can say increment counter, right? It's basically this dot counter plus plus. Yeah, so new counter initially it's at 0. Now let's say thread 1 new thread counter dot increment counter. Let's say this happening in uh, for int I equals to 0, I less than 1000, I plus plus. So here the thing is basically we are not performing a synchronizer one, we are using atomic integer, like atomic integer. Let's say thread 2 and thread 1. Thread 1 dot start and thread 2 dot start. So we can basically wait both to complete. Thread 1 dot join thread 1 dot join thread 2 dot join. You can basically catch interrupt exception, right? Let's for now let's okay. So s out thread interrupt exception e. So for now let's counter dot get counter, right? So what will happen here, obviously things won't work. We get expecting 2000, but it will get more than either more than 2000 or less than 2000. Yeah, 1300. This is wrong, right? So generally what we will do, we apply synchronization on top level. That is basically obviously solved, which we already discussed previously also. So that is solved, right? Every time if you run it will get 2000 only. Now basically let's apply atomic integer. How atomic integer will basically, without applying synchronization, how to make sure through atomic integer it can be modifiable, like see atomic integer counter dot equals to new atomic integer, and you're passing this counter, whatever initial value, it's always 0. Okay, this dot, yeah. Okay, fine. Now we basically returns the return integer only. Let's return integer only. What counted dot get, and here while here we basically apply counted dot compare get and increment, right? There is a method called increment get and increment. So what it will do, it's internally performing the two operations, basically adding the value plus one in a most atomic way. Like, so here if you execute this program, you'll always get the 2000 only. Like, here we didn't apply synchronization, we're applying atomic integer. Through atomic integer we are performing the operation, and we always get this 2000, right? So this is nothing but advantage of basically atomic integer. So for example, even though, let's say, okay, now let's try volatile as well. Let's say volatile int counter equals to 0. Let's say counter v, because I don't want to disturb this. Counter v equals to counter only. So now here let's apply counter v plus plus, right? Let's do another get call also. Get counter v. This will return the counter v value. So now if you perform if you do this system.out.println, right, counter dot get counter v. So now then, so compare and set always works for 2000 only, but this value, volatile value, won't work. See, because it's guarantees the visibility, but it's not able to update it's not able to perform this compounding operation. So that's where actually solving by the counter, by the atomic integer atomic boolean, it will solve both the visibility as well as the count as well as the compounding operations, atomic operations also, like. So this is basically a overview of basically what is atomic integer, what is atomic and also volatile. In the next video, we will discuss very in depth about Java logs, where we will see about reentrant logs, read-write logs, semaphores, with every examples and real world scenarios. So if you like the video, so please like and subscribe and share to your friends. If you have any doubts, please feel free to comment. I'll reply to every comment. So we'll soon meet in the next video. Till then, bye bye.